Federal scientists don't call it the most dangerous volcano in the country because it erupts the most often. It doesn't. They call it that because of exactly where it sits, towering over a metropolitan area of millions of people with enough ice and glacier packed onto its slopes to bury entire towns if that ice ever gets mobilized in the wrong way. And just over a year ago, that mountain produced the single largest earthquake swarm ever recorded in its history. Over 1,850 located quakes and thousands more too small to pinpoint, shaking the ground beneath it for weeks straight. This is the story of Mount Rainier, and what scientists actually found when they went looking for answers underneath it. Today, we're breaking down the record-breaking swarm, what caused it, why federal researchers flew a helicopter through the volcano's own gas plume to figure out what was really going on and why. Even with the alert level sitting at normal the entire time, the U.S. government has been quietly pouring new monitoring infrastructure onto this mountain. No fear-mongering, just what the USGS Cascades Volcano Observatory is actually saying. If you live anywhere near Seattle or Tacoma, this is a story you genuinely need to understand. Drop a comment and let me know. Had you heard about this swarm before today? And if you want to keep tracking Cascade volcano activity, subscribe right now. It's free. Let's get into it. Before we get into the swarm itself, it's worth understanding why Mount Rainier holds this specific, unenviable title in the first place, because it's not about eruption frequency at all. Rainier is the highest peak in the Cascade Range, rising 14,410 feet above the Puget Sound lowlands, and its slopes carry more glacial ice than any other single mountain in the contiguous United States. That combination, a genuinely active volcano wrapped in enormous amounts of ice, sitting directly above densely populated valleys, is exactly what makes it so dangerous. The specific hazard scientists worry about most isn't lava, it's called a lahar, a volcanic mudflow. When heat, ground shaking, or even just gradual weakening of rock on Rainier's slopes destabilizes portions of that ice and loose volcanic rock, the resulting flow of mud, debris, and water can travel for dozens of miles at highway speeds, following river valleys straight down into communities like Ording, Puyallup, and Sumner, towns built directly on top of the deposits from past lahars. The most massive of these, the Osceola mudflow, happened roughly 500-600 years ago, carried more than 3 cubic kilometers of material, and reached all the way to what's now Puget Sound, burying the very ground that some of these communities sit on today. A more recent event, the electron mudflow, happened around 500 years ago. This is exactly why Rainier ranks among the handful of volcanoes the USGS classifies as very high threat nationally, not because it's constantly erupting, but because of the sheer number of people living in the path of what could happen if it does. On July 8th, 2025, at 1:29 in the morning, seismic instruments around Mount Rainier detected the start of an earthquake swarm, a cluster of quakes happening close together in both time and location. Within hours, the rate had climbed to over 40 located earthquakes per hour. By the time scientists at the USGS Cascades Volcano Observatory and the Pacific Northwest Seismic Network finished analyzing the data weeks later, they'd located more than 1,350 individual earthquakes, with thousands of additional events detected, but too small to precisely locate. Using a technique called template matching, which identifies repeating earthquake families with nearly identical waveforms, researchers eventually identified roughly 800 distinct events total. To put that number in perspective, Mount Rainier typically produces around 9 to 10 earthquakes per month as background activity, and the volcano has experienced small swarms once or twice a year for decades, usually far smaller events. The previous record holder was a 2009 swarm that produced just over 1,000 earthquakes over 3 days, with a maximum magnitude of 2. 5. This new swarm blew past that in every measurable way: total events, hourly rate, and total energy released, making it, in the USGS's own words, the largest earthquake swarm ever recorded at the volcano. And yet, through every single day of that swarm, the volcano alert level and aviation color code for Mount Rainier stayed at normal and green, the lowest possible designations. That might sound contradictory, a record-breaking swarm and a nothing to see here alert level at the same time, but understanding why requires looking at what scientists were actually watching for. Here's where this story gets genuinely interesting from a scientific standpoint. When earthquakes start happening beneath a volcano, the immediate question every volcanologist has to answer is simple but urgent. Is this magma moving, or is this something else? To figure that out, the USGS Cascades Volcano Observatory did something that hadn't been done at Mount Rainier in 27 years. They flew a helicopter directly through the summit's volcanic gas plume. On August 4th, 2025, USGS gas geochemists partnered with the National Park Service to conduct an airborne survey, using an A-STAR helicopter equipped with sensitive gas detection instruments to sample emissions from small steam vents called fumaroles in Rainier's east and west summit craters. The logic behind this approach is genuinely elegant. When magma rises toward the surface, it releases specific sulfur-based gases, sulfur dioxide and hydrogen sulfide, gases that essentially act as a chemical signature of molten rock on the move. The helicopter survey detected water vapor and carbon dioxide in the gas samples, but critically, no meaningful traces of those sulfur compounds. Combined with GPS data from the geodetic network showing no unusual ground inflation or deflation throughout the entire swarm, and no changes in infrasound or webcam observations, the evidence pointed clearly toward one explanation. The swarm wasn't caused by rising magma at all. It was caused by Rainier's hydrothermal system, essentially underground water heated by the volcano circulating through pre-existing cracks and fault networks in the rock roughly 1.5 to 4 miles beneath the summit, creating localized stress changes that triggered thousands of small earthquakes as fluids moved and shifted pressure along those faults. Here's the part that should genuinely change how you think about a phrase like alert level normal. Normal doesn't mean nothing is happening underground. It means whatever is happening falls within the range. Scientists consider background activity for this specific volcano, and Rainier's background activity, it turns out, is considerably livelier than most people realize. The volcano recorded over 500 small earthquakes in 2024 alone as part of routine background seismicity, before this record swarm even began. The hydrothermal system that triggered the 2025 swarm has continued operating beneath the surface ever since, and USGS scientists have explicitly noted there remains a real, if small, chance of brief increases in seismic activity in the months and years following the main swarm, simply because the underlying hydrothermal processes may still be active at levels too subtle to generate easily detectable seismicity. By August 25, 2025, seismologists determined that earthquake rates had gradually decreased back to Rainier's typical baseline, decayed to fewer than one located event per day, down from a peak of 41 per hour at the swarm's start. But gradually decreased to normal is a very different story than nothing happened here, and it's exactly the kind of nuance that gets lost when a story like this only makes headlines for a week before disappearing from the news cycle entirely. While the swarm itself has faded from headlines, the institutional response to it hasn't. In the time since, federal officials have continued expanding Rainier's monitoring infrastructure specifically around lahar detection, the mudflow hazard that makes this volcano so uniquely dangerous to the communities below it. New monitoring stations have been installed to strengthen the early warning network that gives downstream communities crucial extra minutes to evacuate if a lahar ever does begin moving down one of Rainier's river valleys. Interior Department officials have personally toured these new installations, and the region continues to host what's described as the world's largest lahar evacuation drill, a recurring exercise specifically designed to prepare schools and communities in the shadow of this mountain for the exact scenario scientists worry about most. This tells you something important about how seriously agencies treat Rainier, even during a period when the alert level never moved off normal. The record swarm didn't trigger panic. It triggered a helicopter gas survey that hadn't been conducted in nearly 3 decades, a wave of new scientific publications, and continued active investment in the physical infrastructure needed to protect the roughly 150,000 people living in mapped lahar hazard zones downstream. There's a specific detail buried in the seismic data that deserves its own explanation, because it's part of what made this swarm scientifically fascinating rather than just numerically impressive. Using template matching, seismologists at the Pacific Northwest Seismic Network identified 48 distinct repeating earthquake families within the swarm, groups of earthquakes that produced nearly identical seismic waveforms, occurring over and over in the same tiny patches of rock. Repeating earthquakes like this are a well-documented signature of fluid movement along a fault. Essentially, the same small patch of rock rupturing again and again as pressurized fluid works its way through a fracture network, rather than the more chaotic, spatially spreading pattern you'd typically expect if a body of magma were physically forcing its way upward through solid rock. Finding 48 separate repeating families within a single swarm gave researchers a genuinely detailed picture of exactly how fluid was moving through Rainier's shallow hydrothermal plumbing system in real time, almost like watching water find new paths through a maze of underground channels, one small rupture at a time. It's the kind of granular, high-resolution seismic story that simply wasn't possible to reconstruct during smaller, less instrumented swarms in decades past. And it's a direct product of just how dense Rainier's modern monitoring network has become. It's worth understanding where Rainier sits within the broader landscape of American volcano monitoring, because it isn't being watched in isolation. The USGS Cascades Volcano Observatory oversees the entire chain of Cascade volcanoes across Washington, Oregon, and Idaho, and maintains a formal threat ranking system based on both eruptive history and the population and infrastructure exposed to each volcano's hazards. Mount Rainier sits in the observatory's very high threat potential category, a short list that also includes Mount St., Helens, Mount Hood, Mount Baker, Glacier Peak, and Crater Lake. Of all of those, Rainier consistently draws the most attention specifically because of its proximity to the greater Seattle-Tacoma metropolitan area, a population center of well over 3 million people, far larger than what surrounds any other Cascade volcano on that list. That context matters for understanding the government's response to last year's swarm. A record-breaking earthquake sequence at a remote Cascade volcano with few nearby residents might warrant scientific curiosity without much urgency. The same swarm happening at Rainier, sitting less than 60 miles from downtown Seattle with hundreds of thousands of people living in its shadow, warranted a helicopter gas survey within 4 weeks, extensive public communication from CVO and PNSN scientists, and continued expansion of the Lahar warning network in the months that followed. The response wasn't proportional to the swarm's size alone, it was proportional to exactly who lives downstream. It's also worth understanding what active volcano actually means for Rainier specifically, since it's genuinely different from the picture people carry around from watching news coverage of places like Kilauea or Fuego in Guatemala. Rainier's most recent eruption with strong geologic evidence occurred roughly 1,000 years ago, and even that event was relatively modest by Cascade Range standards. There's some evidence suggesting minor steam explosions may have occurred as recently as the 1890s, though the evidence for that is considerably less certain. This is not a volcano that erupts every few years, or even every few decades. It's a system that can sit quiet on the surface for centuries at a stretch, while continuing to host exactly the kind of hydrothermal circulation that produced last year's record swarm. That gap between long eruptive silence and genuinely dangerous volcano is precisely what makes Rainier such an unusual case study. Its danger doesn't come primarily from the likelihood of an imminent eruption. Current data gives no indication one is coming. It comes from the simple, unavoidable physical fact that an enormous mass of glacial ice and loosely consolidated volcanic rock sits directly above valleys now filled with tens of thousands of homes. And even a relatively modest disturbance, whether from a large earthquake, sudden heat, or gradual slope failure, could theoretically remobilize part of that material into a lahar with little advance warning. That's a fundamentally different kind of hazard than watching for the next eruption. And it's why the Lahar Detection Network, not the eruption forecast, has been the primary focus of new government investment in this specific mountain. So here's the honest, complete picture. Something did genuinely change beneath Mount Rainier, the largest earthquake swarm ever recorded at the volcano, driven by hydrothermal fluid movement rather than magma, confirmed through gas sampling, GPS data, and seismic analysis working together. That swarm has since subsided back to background levels, and there's no current evidence of magma moving toward the surface. But the underlying hydrothermal system that caused it remains active. Scientists say brief future increases in seismicity remain possible, and the mountain's fundamental hazard, the lahar risk to communities built in its shadow, hasn't changed at all, which is exactly why monitoring infrastructure keeps expanding even during a period of official calm. If you live in Western Washington, particularly in the Puyallup River Valley communities directly downstream of Rainier, the practical takeaway isn't panic, it's awareness. Know your community's lahar evacuation route, because those routes exist and are specifically designed for exactly this scenario. Pay attention to Volcano Notification Service alerts if you want real-time updates. And understand that alert level normal at a volcano like Rainier doesn't mean inactive. It means scientists are watching extremely closely and haven't yet seen anything crossing the threshold into genuine concern. One final number worth sitting with. Roughly 150,000 people currently live within mapped lahar hazard zones downstream of Mount Rainier, in towns whose land was quite literally formed by past mudflows off this exact volcano. The Osceola mudflow 5,600 years ago, the Electron mudflow roughly 500 years ago. That's not a hypothetical population at risk in some distant future scenario. It's the actual number of people whose communities are built directly on the geological evidence of what this mountain has already done more than once. Understanding that is the entire reason a swarm of small magma-free earthquakes deep beneath a glacier still earned a helicopter survey, dozens of new monitoring stations, and a permanent place on the federal government's very high-threat volcano list. We're going to keep tracking Cascade volcano activity as new research comes out. Subscribe so you don't miss it, and drop that comment. Did you know Rainier's danger came from mudflows rather than lava? Thank you for watching, and I'll see you in the next one.